All right. Well, thank you all for joining for today's finale to our 2024-2025 seminar series. We're thrilled to have with us Professor Sylvia Herbert from the beautiful UC San Diego. She's an assistant professor there in mechanical and aerospace engineering. Prior to that, she had got her PhD at UC Berkeley, working with Claire Tomlin on different aspects of safe control, and continues to push the boundaries there, recently receiving an ONR Young Investigator Award for her work. Congratulations. And many other paper award recognitions. Also of note, potentially for this group, she's one of the inaugural co-chairs for the new TC on robot control that we think would be of interest to many of those in our TC as well. So I encourage you to check it out. Today, she's going to be talking about some generalizations of the celebrated Hamilton-Jacobi Bellman equation to address problems in reachability for safe control, and looking how to address the curse of dimensionality in that domain. So very much looking forward to it, Sylvia.
Thank you so much. All right. Hello, everyone. As mentioned, my name is Sylvia. I'm going to give this talk. It's mostly fairly new slides. So if there are things that are unclear, please just go ahead and interrupt me. So with that, today I'd like to talk about kind of two projects, and they're largely driven by my PhD student here, Will Sharpless. These would not exist without him. And he's been aided by some of my colleagues, Professor Yatin Chow from Applied Math at UC Riverside, and Professor Solmal Bansal from Aero Astro at Stanford, along with his student Zeyuan. I have several PhD students. Again, Will is the main one on this particular work. Part of their job is mentoring undergrad and master students. We're very lucky that at UC San Diego, we're something like 35% first generation undergraduate students. And so we take that pretty seriously. And none of the PhD students have graduated yet, but some of the undergrads have now gone on to academia or industry. All right, but onto the talk. So we're going to talk about differential games. Differential games occur all the time in robotics and other applications. Be very useful to reason about differential games so you can think about robust optimal policies and paths despite these other players. The challenge, of course, is that solving this at scale is really hard. And so for many of these applications that we'd like to be looking into, they're just not very tractable if you want to deal with nonlinear games, bounds on inputs, and many practical aspects that you see. So that's kind of the main motivation of what I'm going to be talking about today. First, we're going to go into some background, and then we're going to go into the actual two topics that I want to discuss. The first background, we're going to talk about Hamilton-Jacobi reachability analysis. This is essentially fancy dynamic programming in order to solve these differential games. Then we're going to go into the Hopf formula, which was recently created or recently revamped by Stan Osher from Applied Math at UCLA for solving linear reachability games. Then we'll talk about how we modify this in order to deal with conservative solutions for high-dimensional nonlinear games, and then how we more recently are doing linear semi-supervision for learning these PDEs. And so this work is in CDC and is submitted to TAC, and then this work will show up at L4DC this summer and was just nominated for our best paper. Okay, so let's talk about some of that background. So let's assume that I'm given some dynamical system. I have a state, I have control and disturbance. This could be some general nonlinear system. I'm assuming that these are compact sets. So I have actuation limits on my input and my disturbance. Then we can roll out a trajectory. We're going to start at an initial state X, roll out that trajectory according to our dynamics, where we are going to assume that the control signals, rather than control actions, are measurable. So we roll those out, we play the control and the disturbance, and then we reach our endpoint. Here, I'm using this compact form for trajectory notation. So this is saying, take in the initial state, the initial time, and apply control signal U and D, and then query where you are along that trajectory at some time tau, and this will output the state. Okay, again, interrupt me if there's any questions on notation. All right, now let's say that I have some goal, some target in my state space. It doesn't necessarily have to be convex. I'm just drawing one for ease, I guess, here. We want to determine the reachable set. Informally, before I show the math, the reachable set are the set of initial conditions for a particular initial time, t, such that I can reach my goal within that time horizon, the target math cal t here, despite worst case disturbances or worst case player actions from the other player. So it's a set of states such that for all actions from the disturbance, there exists a control signal such that my trajectory at the end of time is inside of the target. Note a couple of odd things here. First, this crazy looking D here indicates that the disturbance draws from non-anticipative strategies. If you don't know what that means, don't really worry about this. It just means that the disturbance can't see the future for the control signal. It's a fairly common sense thing that requires some complicated math in order to say it in theory. And then the second thing here is that I'm kind of flipping my time horizon. So my time starts at some negative time t and then ends at 0. So my trajectory starts at a negative time, ends at 0 at the final time. This is because we're doing dynamic programming backwards in time, so it's easier to think about starting at 0 and then iterating backwards. Okay, but we have some target. We want to compute this reachable set. How do we go about computing this? Well, the most kind of general approach that I was trained on by Professor Claire Tomlin is to use dynamic programming. And so the steps are, first you define that target, t, and then you define a target function such that the function is negative inside the target and positive outside. You can think of this as a cost. So it's good to be inside of the target, low cost, and it's bad to be outside the target, high cost. In fact, we're going to define our cost function as just that. So our cost function is going to be given an initial state and time and our control and disturbance signals. We're just going to query the target function at the end of the time horizon. And so at the end of the time, if you're inside the goal, this cost will be negative. At the end of the time, if you're outside, the cost will be positive. So yeah, there you go. And this is for any particular U or D signal. And this is just what I said. And then we're going to define the value function for this cost. So rather than querying any particular U or D signal, we're going to ask for the optimal one. So here we're going to say that we assume that the disturbance is trying its best to maximize this cost and drive you outside of the set, and the control is trying to minimize this cost and keep you inside. And so under the optimal control, now you can ask, will the value function be positive or negative? Here, here I'm just throwing in, for the cost function, I'm just going to directly plug in this target function. So now if the value at an initial state and time is less than 0, that means that the optimal trajectory will end up at a negative cost at the end of the time horizon. And therefore, my my initial state will be in the reachable set for that time horizon. Okay, so this is the value function that I would like to solve. It gives me this nice mapping from my initial states and time to what I will get at the end of the game. Actually solving this can be challenging, non-convex, nonlinear, etc. And so the way that we do it is dynamic programming. We can prove that the value function is the viscosity solution of the following PDE. This is just the PDE version of the Bellman backup, essentially. So the change in value backwards in time is going to be based on the gradients, the spatial gradients of the value function, interproducted with your dynamics, where your control is going to try to minimize along these spatial gradients, try to do gradient descent, and your disturbance is going to try to maximize, try to do gradient ascent. This is our Hamiltonian, and we're going to write it as H. And then we're going to set this terminal condition that at the end of the time horizon at 0, our value is just the same as our target function. So this can be solved via dynamic programming backwards in time. No fancy tricks here. We grid up the state space and we update this PDE at every single point in that space at every single point in time and evolve this. And so if I'm evolving this backwards in time and considering longer and longer potential time horizons, this is what the value function looks like for some random set of dynamics I set up. So this would be my value function for a time horizon of 10 seconds. And so where the value function here is negative, that's associated with initial conditions from which I can reach my goal within 10 seconds despite worst case effort from the disturbance. So therefore, if I just slice this at 0 and flip it around, this is my reachable set, the set of states for which I can reach the goal despite worst case disturbances at the end of my time horizon. Any questions so far? Okay. This is nice. We've been using it a lot. I do a lot of quadcopter stuff, and so we've been using for lots of different tasks of planning and navigating in different types of arenas. It's nice because you get these safety guarantees and you get these control policies associated with them. Compared to using something like LQR, ILQG, MPC, the main pitch is that you can do this long horizon on linear safety. You can get the optimal solution despite the antagonism with bounded inputs from both the control player and the disturbance player. And then the pitch for compared to zonotope or hole methods is you can modify the value function that you're solving in order to generate things like control Lyapunov or control barrier functions. I have a whole other section of research on that I'm not going to get into today. And you get an optimal controller out of this. So you can actually follow the gradients of your value function over time in order to generate the optimal control to reach your goal or avoid an obstacle. And because we're just doing brute force dynamic programming, we can handle weird shaped goals, we can handle weird nonlinear dynamics, we can handle interesting errors. The main issue is exactly what Patrick mentioned even before we started, is the fact that we're gridding up this space and solving dynamic programming. So it struggles with complex models and uncertain environments. And what I mean by this is, again, the dynamic programming issue. And so as we scale up the dimension that we're trying to solve, it gets exponentially harder to compute. And so instead, you'll see people doing these like guarantees over instead of a full quadcopter, like a very simplified model of one, or instead of a more sophisticated model of a car, a little Dubin's car, or if you're trying to think about how a human might move, you might treat them as like a double inverted pendulum, which is clearly does not capture everything that a human can do. And so doing an analysis over this might not be all that meaningful to the true system. And then the uncertain environments. In some ways, sure, we can handle uncertainty. I mentioned that we can have this disturbance that is bounded, but you have to know what these bounds are ahead of time. And these bounds may be overly conservative if you assume worst case possible things, or not conservative enough. Additionally, we can handle obstacles. We can even handle moving obstacles in the environment. I think it's really beautiful, and we can scale up the number of obstacles very easily and then compute what's called like the reachable set for reaching the target while avoiding any obstacles in the meantime. But I mentioned this can take forever to solve if you have a high dimensional system. And so if I don't know how my obstacles are going to move ahead of time, if they're like people, for example, you can't just pre-compute exactly how all these people are going to move. So we can struggle a bit with uncertain environments, largely, again, because of the inflexibility of adapting quickly because of this pre-computing step. And this is, again, showing that as we increase the number of system dimensions, the fidelity of the model, it becomes pretty intractable pretty quickly. So, and again, this because we're gridding up the state space. So in one dimension, if we grid it up versus two, we have a square versus three, we have a cube, et cetera, et cetera. The dynamic programming and stepping the PDE must solve at all points here. Even if you only really care about, where you are locally, you need to solve the value function everywhere in this space. There's a lot of approaches to working on scaling this up. I have many wonderful colleagues. We've been working on things like decomposing systems across space and time. There's a large push on doing reinforcement learning-based approaches, supervised learning-based approaches, and then novel formulations for specific types of classes of dynamics where you can do something clever on the optimization side. Today, I'm going to be focusing mostly on these two, starting with the latter one. And that brings me into introducing this Hopf formula from Stan Osher. Before I get into that, any questions? Okay. Again, this is my first iteration doing this. So I don't know how clear what I'm saying is. So again, the dynamic programming, we must solve at all points. The main appeal of the Hopf formula is that we can allow computation with only one point, only locally. Now, there's no free lunch. There's a lot of reasons why we can do this. we start in 2000 where we have a very restrictive assumptions, which is that the target function is convex. Okay, sure, we need circles to reach, that's fine. But H is also convex and not dependent on X. The Hamiltonian does not depend on the state at all. This essentially means that your state dynamics do not depend on the state, which is a pretty wild assumption for any real systems. Nevertheless, if you do this, then you can solve this formula, which has a few notable things about it. First, it only depends on one point in space. You solve a convex non-smooth optimization problem with ADMM. Note the target and Hamiltonian must be convex. This essentially means that you must have more control authority than disturbance authority. This provides you with a convex value function that makes this easier to solve. And the Hamiltonian, and thus the dynamics, must be state independent. And so because of this, this formulation was not really applied to many things. It was only recently that Stan Osher and Yatin Chow showed that you can do a clever change of coordinates in order to apply this to linear systems, linear time varying systems. So in 2017, they recognized that this extends to linear systems by this change of coordinates. So essentially you take your linear system and you embed how it varies in space into time using this exponential. And then you can plug that in. And so you have a state independent system where the evolution state is encoded into time here. And thus you can solve this problem for the linear systems using that change of coordinates. So this is great for still linear time varying systems. If we just check this looking at system dimension, my student Will built up this nice little Julia package that shows time per point on our currently fastest dynamic programming software that's GPU optimized versus solving Hopf. Again, for linear time varying systems though, so no free lunch here. Okay, so that's the background on that. Now we can start jumping into things. So this Hopf formula, the linear version of it came out in 2017. There's been some really interesting works on using it, but largely for linear systems or systems which can be iteratively linearized, feedback linearizable, this kind of thing. We wanted to know if we can apply it to more general nonlinear problems. And for that, we're going to get into how we can solve the game, the linearized game, but with conservative guarantees on the true nonlinear game. Okay, so we have some target set. We'd like to find the backward reachable set. And the pitch that we had was that for any linear model on a compact set, we can represent the nonlinear system as the linearized dynamics plus some error term. So just think of linear plus error. You have your linearization error, sure. If we can bound this set, then we can try to determine what is that maximum linearization error over this set for the nonlinear system. We can then treat this error as an antagonistic player in our game. So let the game with the linear dynamics and an antagonistic error be given as this. So now it's just an additional disturbance that works with the other disturbance to try to mess you up in order to keep you from reaching your target set. A very simple idea. Now your Hamiltonian for the linear system, we're going to say we're going to take the max over error of the Hamiltonian of your nonlinear system. This is equivalent to saying your Hamiltonian for your linear system plus the max over error of your costate times the error. And then the actions of this new player are going to be bounded by that true maximum error. So again, it's going to be drawing from its input bounds, where its input bounds now are up to the worst case error, linearization error over this set. Now, how do we get the set? How do we bound the error, etc.? Let's go through those steps. I guess first, if there's any questions on this, this is the main idea, but I think it's pretty simple. But I don't want to claim that if there's questions.
Super cool.
Okay.
Yeah.
Okay.
So if
All
anyone
right.
has questions, they can use the
Yeah.
you can
It's fine if not. I just want to make sure that people are following.
yeah, just as a matter of practice. If folks do have questions at any point, feel free to use the React button here in Zoom and raise hand.
Okay, sure. Yes, I'll stop asking if you guys promise that you will interrupt me.
Very good. I love the visuals so far.
Oh, good. Okay, so the first thing we need to do is find this set of what we call, oh, sorry, my toddler is knocking on the door. My husband must not have acquired him. Sorry, one second. You know? Yeah. Go with dad, okay? Sorry. All right, okay. Um, so we want to find the set of what we call feasible states. The feasible states are the states where the disturbance and control are cooperating. So we actually treat the disturbance as working with the control. And so there's no game anymore. It's just an optimal control problem. And you can use this, for example, using zonotope method. So this is the set of feasible states for which there exists some control and exists some disturbance that together can try to drive you into the target. You can over-approximate the set, as I mentioned, pretty rapidly using zonotopes. And you know then that if they're working together, if this is the largest set in which they can be start within and reach the target, that then the differential game version where they're not or no longer working together must be contained inside. And so you know that the true reachable set is somewhere inside of this. And so if we do the linearization error over this larger set, then we should know that it should be applicable to the smaller one inside. We then define the maximum linearization error over this feasible set. For different ways of doing the linearization, this can be very easy to compute. For other ways, it can be harder to compute. This linear game with antagonistic error is now going to be conservative and can be solved with the Hopf formula. When we solve the linear dynamics with this antagonistic error, we know that the solution, the value function, will be greater than or equal to the true nonlinear one. So if this is our true nonlinear value function, the one that we compute with the error won't be able to expand as much because the disturbance will work against it. This means we'll have conservative reachable sets. What I mean is that where they're equal 0. So again, if we slice the value at 0 and show what that might look like, and then slice this value at 0, this one is going to be contained within this one. It will be an under approximation of the true reachable set. Additionally, and this is the one part that I find more useful, is that the resulting linear control that you get out of the Hopf formula will succeed in reality. So you know that if you apply the optimal control on the linearized game, that you will, as long as you start within this set, you will be able to reach the target set. So we might not be able to recover the full thing, but we can at least provide guarantees on if you start here, you can reach the goal for this nonlinear problem. And we can do this super fast online. This is it written out in the theorem version, but it's right, it's saying the same thing. So saying that we can ensure that the value function for the linearized system will allow us to make sure that we capture the value function for the nonlinear system, and that the resulting optimal control will be able to put you into the target. So here's some initial tests that we did. So just on a simple 2D system, just to start with a toy problem, here's our target set that we want to reach. Here is the feasible set, the set of states for which if the control and disturbance are working together, they can reach the target set. We define the error over that. And this is also our comparison in terms of if you ask why not just use zonotope methods. In orange is then the true reachable set. And then in green is the under approximation that we're able to get. So we can guarantee that we have this conservative under approximation for reaching this target. If instead you flip this and the target's now something the disturbance wants to reach and the control wants to avoid, then we can guarantee that we will over approximate the set of unsafe states. So now this is the set of states for which the disturbance can drive you into the obstacle, and we over approximate that set and provide you with a control to avoid that. Now, this can be fairly conservative, as you see. So we also worked on a few different methods for reducing conservativeness. I'm not going to go into the details of all of them, but for those who might be interested, we can try to, rather than thinking about the linearization error over the full space, if we think about the feasible set, how it grows in time, we can think about the linearization error as time varying. because we can handle things that vary over time, just not over space with the Hopf formula. We can think about what happens when we only apply disturbance for computing the over approximations and still be able to retrieve the conservative sets. We can do ensembles. So if you linearize around different points, you know that each one will provide a conservative approximation. So you can then take the union or intersection as appropriate. And we can partition. So we can split up the goal into different areas and ask how do we reach these different parts of the goals or avoid different parts of the obstacle. And then you can take the union of all of those. And then we apply this to a game where we have 6 agents. Here it's 15-dimensional. If we use the zonotope methods, here we have an evader that's trying to evade all of these pursuers that's facing it. Here I'm projecting down the zonotope holes for each of the pursuers, and it seems like you cannot evade capture. This is because, again, they over-approximate these sets. However, if we then define that linearization error over this and then do the Hopf formula, we can indeed find places for which we can evade capture, and we compute this control policy on our PhD code in 300 milliseconds. We're actually working with some colleagues at China Lake Naval to maybe see if we can get this a bit faster on an FPGA. Okay, so that's nice. We can now linearize the system. We can solve online the controller for how to try to reach a goal or avoid obstacles. And we can know that that gives us conservative guarantees on the true nonlinear system if we then roll it out on the true nonlinear system. The next question was just, are we doing the right linearization? Again, this might be really conservative if you have some funky nonlinear system to just try to linearize it and then do the game on the linearized system with this huge linearization error. And so the question was, can we reduce that linearization error by lifting to a higher dimensional space for which we have more flexibility in how we do our linearization? So if we have some, 3D nonlinear model, can we lift it to a 10D linear space, or some 15D nonlinear model, can we lift it to a 30-dimensional space, where we then find the linearization and then solve the game in this higher dimensional space, but project it back down onto the lower dimensional nonlinear space. So yes, we found a particular lifting mechanism for which we can do this. So if you consider this augmented space and this lifting function of this form where we retain the original state space, but then we add these additional dimensions, then we might be able to improve the accuracy of a linear model. And there's lots of people who work on these kind of Koopman type approaches. And in this case, we can say that if we can, again, bound the error between our nonlinear system and our lifted linear system, then when we project back down, we can guarantee that we'll remain conservative with respect to the true nonlinear system. This is kind of what it looks like visually, again, on a simple problem so that we can see, because we only see in 3D. So here, if this is the target set in the 2D nonlinear space, if we lift it to this 3-dimensional space, we then have this target set that's now like a cylinder. And if we solve the game in this 3-dimensional space that's linear, and then project down the solution, the projected down solution is this dark purple one. This is the reachable set for reaching that target, and it's guaranteed to be an under approximation of the true reachable set, which is in the light purple. And so we just now explored that. We just submitted it, this work to CDC, and now we haven't actually used it on any real systems. So thus what I was mentioning of trying to find some crazy people who have strange nonlinear robots to test this on. Okay, so that's that one. So this is, we want to stick with these hard guarantees. We want to be able to say under certain classes of systems, we can guarantee that we'll have these conservative approximations along with the controllers, and we can solve them pretty fast online. If we are willing to relax ourselves a bit in terms of the hard guarantees, are there ways in which we can take advantage of data-driven methods with this Hopf formula together? And this gets into the linear semi-supervision for learning HJB PDEs. And I'll pause for just a second, see if there's any before I jump in. Okay. So for this, I'm motivated by my colleague Solmo Bonsall at Stanford. He has this thing that he calls deep reach, which is this physics-informed neural network. So essentially trying to learn the solution to the value function using a PDE loss. It's nice because it scales with the complexity of the underlying solution rather than with the number of state variables. What I mean here is that if you have a fairly simple problem where the value function looks relatively convex and nice, it's kind of easy to fit a neural network to that. If you have a really funky problem where the value function is like all over the place, like a weird reach avoid problem with lots of nonlinearities, then it's very hard to, with a function approximator, fit to that type of function. And so strangely, on really low dimensional problems, deep reach can do quite poorly if it's a very funky problem where I don't have a good way of defining funky exactly except for this complexity. However, for like nicer structures of problems, it can solve very high dimensional ones quite easily. But again, it can struggle with these learning errors for some of these more interesting nonlinear games. Oh, and one other thing is that we can estimate the learning error and use it to provide probabilistic safety assurances using conformal prediction type of methods. So we lose hard guarantees. We can do some conformal prediction-based probabilistic guarantees. Okay, so we're going to now define a neural approximator, so V sub theta, where theta are going to be the parameters of the neural network, defined by this here, where the activation functions here are going to be sinusoidal. So this is the ith layer of the neural network. This is the weight matrix, and this is the bias. And then to train this approximator, they use a PDE loss. And so they have that this, the loss is based on the expectation of the PDE loss of the parameters, where this is just going to be taking the change in your value over space and time and adding the Hamiltonian. So essentially trying to make sure that that PDE gets as close to zero as possible. Where this T here is an increasing time range. And so you work within small windows of time as you work backwards in time, very similar to the dynamic programming. The challenge is that this can suffer from the complexity of optimizing the PDE loss, and the approximations can deteriorate as we increase in complexity and dimensionality, that kind of thing. We can still get those probabilistic guarantees, but the conformal expansion you have to do can be really ridiculous in some cases to try to get those guarantees. So the idea was, we can compute this linear value function using that Hopf formula. It's not going to be the true nonlinear solution, but could it at least nudge the learning process in the right direction? So this is just pasting again the Hopf formula. I'm going to use this fancy H here for describing using the value function for the Hopf formula, given a particular target function and a linear Hamiltonian. And the question is, can we use this to guide the computation of the nonlinear value function via the semi-supervised learning? And to do this, we need to think a little bit about the relationship between the linear value function and the nonlinear value function. We by no means worked out all the theory to this, but we've taken a step towards it, where if you represent the Hamiltonian with the linear system plus error, as like we said, the linear Hamiltonian plus or minus here, the maximization over the error. Oh, this should be with the inner product. This plus or minus shouldn't be there. Then we can show that the difference between the linear and nonlinear function can be bounded by taking the problem and adding the error and the problem and subtracting the error. It's very similar to what we were doing before. Now, if our linearized dynamics in the very simple case is defined to essentially just be our nonlinear system plus doing the Taylor expansion here around an operating point, then we have some finite error. Then we can say that our nonlinear value function will be our linear value function plus this error, and this error is bounded. And so, in other words, we can efficiently learn this part of the solution And then we can say something about trying to learn this error term using the PDE loss. So we want to start with the linear solution and then slowly deform towards the nonlinear solution. The way that we are going to do this is going to say that we have this v lambda, where when lambda is 0, we recover the linear value function, and when lambda is 1, we recover the nonlinear value function. The way we do this is that in the Hamiltonian, we say that the Hamiltonian is going to be 1 minus lambda times the linear system plus lambda times the nonlinear system. So again, when lambda is 0, we're just learning the linear solution. And as we change lambda to 1, we start introducing more and more nonlinearity into our dynamics. And then a v lambda here is going to be Lipschitz continuous with respect to that lambda. And we have the proof in the LRDC. And this is kind of what that looks like. So if you take the value function and you start with the linear value function, as we increase the nonlinearity by shifting from the linearized dynamics to the nonlinear dynamics, you can see that we get this funkier shape to the value function. So given the success of the PDE-based loss for training the value function using the normal pin-based methods for deep reach, we propose these following losses. The first is this decayed, let me start with the second, the decayed linear supervision loss. This is going from this linear to nonlinear that we talked about. And then we also suggest this augmented linear to nonlinear semi-supervision, where here now we're going to augment an additional state that brings us from the linear to nonlinear. Where here LS, here is the least linear least squares loss. So again, let me just recap. So we're going to guide the training of the nonlinear value function by starting with the linear solution and then using that as supervised learning because we know the true solution for the linear solution, but then allow it to deform into the nonlinear solution by introducing more and more of the PDE loss. We wanted to test this out on something that was high dimensional, but for which we can still get ground truth. We came up with this little system that we consider as a publisher and subscriber system. So essentially you have this publisher, you can add on additional subscribers in this particular type of format, where as when alpha is 0 and beta is 0, we have a truly linear system, and then we can add more and more nonlinearities by increasing alpha and beta. This is just a toy example for testing this out. The reason why we came up with this toy example is that if we can decompose it, so we can actually then solve it on a bunch of smaller dimensional components and then put them back together so we can look at ground truth. This is what that looks like, just the ground truth of solving this and then recomposing it. So here we have using linear, and then as we change around these alpha and beta terms, you can see that it gets to more nonlinear, funky solutions. Okay, here's us testing it. So on the top, we have the standard deep reach just using the PDE loss. In black, we have the ground truth solutions that we were able to reconstruct. This is for our 7-dimensional benchmark. And then in red is the reachable set that's recovered using deep reach, using just the PDE loss. On the bottom, we have our linear decay method using our approach of going from the linear to the nonlinear. It took less time and it did a better job. Again, no guarantees now on anything ever, but we seem to in practice do better. We then scale this up to a 50-dimensional benchmark, where here, again, we have the standard deep reach, which struggles now that we're getting to 50 dimensions. And then we have this decayed supervision that I mentioned, and then the augmented supervision, just 2 different ways in which we're doing the nonlinear to linear training. Over here, we have the intersection over union, or Jacquard index. This wants to be as close to 1 as possible. If it's 1, that means that you recover the set exactly. The baseline is in red. And then our decay method is in blue, and our augmented method is in green. Our runtime, you see that the augmented method is similar to the baseline, but the decay method is much, much faster. The trade-off is that the error for the decay is a bit higher than the augmented method. So we have now one approach that's very fast, but a little bit less accurate, another approach that is more accurate, but takes more time. And so again, we just this just got accepted to L4DC. We've only tried it out on these types of problems, and so now we're very eager to see if it works on like real robotics problems. The only step that we've taken towards that is looking at some quadcopter navigation type of problem. Here, I think it was a 10-dimensional nonlinear quadcopter model. The baseline here is using standard deep reach. In yellow is the set that's recovered using deep reach. I mentioned that we can do some conformal prediction. So we did this conformal prediction analysis and expanded that set such that we got, oh, I forget now, but like 90-something% probabilistic guarantees. And that's what you see in blue. So this is how much we had to expand the set using the baseline method by rolling out trajectories and doing the conformal prediction analysis. And then when we roll out trajectories, we do in fact see that we get some that crash. If we do our decay and our augmented system, we see the results that we get in yellow. If we do the conformal prediction expansion, you see then what we get around those. And then when we roll out trajectories, we do see occasionally that we do have issues, but in general, we do much better empirically than the baseline method. So with that, we talked about Hamilton-Jacobi reachability analysis using dynamic programming standard-based methods. Really nice because it's very general, but has that main challenge of the cursive dimensionality. We talked about the Hopf formula, which came out of the applied math community, which initially was just for systems that the dynamics don't depend on state at all, was transformed into something where we can deal with linear time-varying systems. And it was really nice in that you can now solve in a pointwise manner these bounded games with the bounded inputs for linear time-varying systems. We then talked about how we can transform them to solving games on the nonlinear system by doing linearization, treating that linearization error as a player in the game that's working against us and getting conservative solutions. We showed that then you could do this linearization in a higher dimensional space so that you can get a tighter linear approximation. And then finally, we talked about how that linear solution that's very, very fast can be used to help guide the training of a nonlinear solution by combining it with the PDE loss that we see in pins. So for next steps on the Hopf side, we want to actually apply this to something where real-time analysis and adaptation is required and conservative solutions are acceptable. And we want to optimize for the best means of lifting that system in order to reduce the linearization error. We did some fairly naive things in terms of how we were doing this linearization, and we feel like we can do better there to reduce that linearization error. On the pin side of things, again, we want to also apply this to something real. And at the end of the day, we're roboticists here, and we want to see if it's actually useful on something. And then we want to further explore this theory for guiding the network from the linear to the nonlinear solution, and have been working with some applied mathematicians on that. And then we've been playing with the idea of extending this to composing multiple different target and constraint sets that I can't talk about too much, I suppose, because my students actively figuring out what that means. And then we'd like to apply it to a few different pin structures. We've been reached out by other people who have different types of pin setups. They think that they can use this approach to help guide the training on their structures. And again, I want to say that the majority of all of this is just my student, Will Sharpless, and we've been assisted very heavily for the lifting stuff and the conservative solutions by our colleague Yatin Chow. He was one of the original people who worked out this switch from the Hopf to the linear system change of coordinates thing. And then we relied on Somol Bonsal and his student Zeyuan to help us with the deep reach side of things and getting started on training that up. And that's the end of my talk. You can find more information at our website or my email. My email is very easy to remember. It's sherbert or sherbert@ucsd.edu. And with that, I am done. Thank you.
Excellent. Thanks so much. Yeah, this is super exciting. It's the idea of using the linearization error as a player in the game is super
Yeah,
clever.
isn't that cute? It's a pretty simple idea, but it works well.
Yeah. And then to see that make to be able to have guarantees with a nonlinear player in
Yeah.
15 dimensional, that's kind of unheard of. So this is
Thank
great.
you. Thank you. Yeah, yeah, we're excited about it. Again, could be crazy conservative depending on the linearization. So that's really where the trick is, how to do that linearization intelligently.
Yeah. I guess I mean on a similar note, it seems like you've got flexibility in how you like encode your reachable or your target set in the first place with that function J.
Yeah.
Do you have a sense of like, are your approximations dependent on that choice? Are there some better choices or worse choices? And
Yeah,
so
yeah.
is there something that guides what is better or worse? Or because it's nonlinear, you just got to try some stuff and see what works out?
No, there's definitely tricks to it. So especially for the lifting thing, the way in which we lift the target, we can do in a couple different ways. I only showed one, I think, in which we kind of lifted the target in terms of this oblong ellipsed type of way. We in the paper we have several different ways in which how you can think about lifting that target to the different space and defining the J in that higher dimensional space. We also had the could you partition the target into different ways in order to try to ask, how do I reach different parts of the target? And that makes it an easier problem in many ways in which you can have several different under approximations for reaching different parts of the target because you linearize around those different parts. And then you can union them all together. We do have some restrictions on that J. I think I mentioned that we have to have it be convex for the Hopf formula. And so how you find the right, yes, transformation of it is something that we are still sorting out. But good eye.
Again, if you have for any questions from the group, you can take them in the chat,
Mm.
or if you would like to speak, we can do that via the raise hand feature.
I guess I can hop in. You know, I think, you know, the thing that you are saying there at the end is very like interesting to me, which is like you have to be very careful with your linearization so that we can get something that's not like crazy conservative. Do you like, I know this is somewhat early in doing all of this, but do you have like hunches, tips and tricks, you know, thoughts on if you have some random dynamical system, right? Like, is there a right approach for how to begin to think about that so we can start to generate problems that are generally better? And maybe that's impossible in the general case, but like, I don't know if there's any sort of guidance.
I don't. One of the main challenges that we're having here is that the Hopf formula, again, we can't have anything dependent on space. And when we talk about linearizing something, the first thing you think about is, oh, like iteratively linearize across space, right? And so we can't directly do that. And so a lot of what we're trying to sort out is are there clever ways in which you can think about linearization across space and encode that into time for certain types of systems, and then try to think about your linearization over time as the thing grows. This has been hurting my brain as we've been trying to think about how to do this well. But in general, this is, I think, the main sticking point for us for what's keeping us from just applying all the ILQG type work to it is that it doesn't directly allow us to do like space varying linearization in space itself. If we want, if I mean, we would then lose the like pointwise solvability of the problem. So that's something that we've been exploring, as well as can you do clever ensemble type of things with your linearizations and trade-off there. So no, it's still very fresh and open, and I have no idea what direction we'll go into or how useful it will be down the line.
No, that sounds cool and fun. I don't know. We've been doing a bunch of trajectory optimization work and finding weird things around, you know, like we always have this is sublinear or linear or quadratic. Like you have some guarantee theoretically, but practically it's all over the place. And I think there's also some like deep confusing theory there around like how do you induce a problem that will be sort of in the right area of descent in the state space. And I think it depends both on the dynamics and the cost. And again, it's these sort of same things. Yeah. I feel like this is coming up all over everything that's optimization
If
and
you ever want to
modeling these
bet
days.
more,
Yeah.
I and my PhD student can certainly go on for a while about this.
No worries.
guess maybe relatedly, um, we have a question. Oh, no, just a thank you in the talk or in the chat. Um, the linearization for the multiple evaders or the single evader multiple captors example, you have like linearization here for each individual agent, but there's less nonlinearity because of the decoupling. Do you have a sense when you go into like higher D coupled dynamics, how these approximation errors will fall out? And I guess maybe the basis for this question is that, like if you go back to some of the sums of squares strategies for regional stability verification and high dimensional robot systems, the like regions that you would get would be very tiny because of the nonlinearities, which made me feel like, yeah, for our humanoids or quadrupeds, uh, any linearization strategy that's not relinearizing can kind of get us into trouble. But then more recently, some of Brian's work or some of Zach Manchester's work on like picking one linearization point and using that for MPC has really, in my mind, challenged some of those preconceived notions. So I'm curious about your thoughts there.
Yeah, so we have not been we haven't yet put this on a dog or anything like higher dimensional and very coupled. Uh, I think that that was one of the main motivators for Will, my student, for the next work, the trying to find some augmented space over which maybe you can find a better fit. And so we're still very much flailing in terms of what is the best approach in terms of how to apply this Hopf formula. This we think will be if we can work out how to do this lifting very well. We found one method for which we can lift and be able to retain these guarantees with the bounded control and disturbance, which in itself is not easy with the Koopman stuff. Uh, but we think that there may be other approaches that we can do here where we can get tighter antagonistic errors as we do this. But yeah, I think that there's a lot that has already been explored, as you mentioned, for trying to handle this, and we have not really fully tried to apply these to our work, but would be very interested if anyone's interested.
Fantastic.
I would say,
Okay.
Patrick, I was also surprised at how well that worked. I was not confident going in that was going to work as well as that worked. Turns out linear control, especially on quadrotors, is pretty good.
Yeah, it really is it feels like gambling. Like you try something, see how well it works. I mean, a lot of it is the power of and like reiterate like NPC type methods are really, really powerful even with, not super accurate models. So
Yeah, well,
there's a
and this is my always thing on like there's this trade-off on like speed and accuracy of your solve, and I think there's really cool, interesting things there, which again, we should lift into a higher dimensionality, and then there's some dynamics there that we don't really understand that will tell us like, yeah, and so this is all I think very related and cool.
yeah, and that leads into some of my other students who are less math inclined are trying to get my student to help like seed their solutions. Again, this whole using multiple methods and doing this trade-off between fast and accurate and like anytime reasoning type of thing. So there's lots to play around with, and the student has a lot of ideas and not so much time before graduating. So we'll see where he goes.
After many years of feeling like we were kind of just bumping up into that dimensionality limit of these tools, it's nice to see kind of more open future for them. So
Yeah, it's exciting. And then my colleagues who work on the more RL side of things are also getting some pretty impressive results of trying to push the dimensionality of this. Again, losing guarantees though. So there's this trade-off here.
okay, well, thank you so much for spending the morning with us and sharing these exciting developments. Um, for those that are watching on YouTube, we hope you'll check out our webpage or our YouTube channel for all of our other talks. And thanks all for participating in our 2024-2025 TC on model-based optimization seminar series. Be on the lookout. We'll be having a social event at ICRA in Atlanta. So hope to see many of you there. So thanks all, and thank you, Sylvia.
Thank you. Bye-bye.